Hello and welcome to our TI Technology webinar hosted by Texas Instruments Australia. We are excited to bring you Circle and Geometric Proofs, Unit 2, Topic 3 from the QCE Specialist Mathematics course with a very experienced mathematics teacher, consultant and TI trainer, Mr. Frank Moyer. My name is John Bayman and I am your host for this event. I teach mathematics to Year 7 to 12 students at Lachlan Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. I just wanted to remind you of the QCE teacher resource books that are available on the TI Queensland website, which have been extremely popular. If you don't have a hard copy as yet, please email teacher-support@list.ti.com and they'll post one out to you. And also to let you know that the General Maths Teacher Resource Book will be available from the end of this month, from the end of July. As a general reminder, tonight's webinar is being recorded and will be available to rewatch or share on our on-demand webinar page on the TI Australia website. Please feel free to send any questions at any time to Frank using the chat window on the right-hand side of the screen, and I'll endeavour to get them answered by Frank. And on that note, it's timely to say I would now like to introduce our presenter this evening, Mr. Frank Moyer. Evening, Frank.
Good evening.
Frank has a vast experience in teaching mathematics, curriculum development, and sharing his knowledge at national and international conferences. Frank is also passionate about rich tasks and the use of CAS to strengthen and deepen students' and teachers' understanding of various mathematical concepts. And as we can see now, Frank has his TI-nspire teacher software open. So Frank, it's all yours. Thank you very much.
Oh, thank you for that introduction, John, and good evening, everyone, and welcome. Well, as John said, my webinar will draw on material from the QCE Specialist Maths Teacher Resource Book for the TI-nspire CX2, which is a resource of 166 pages of learning activities, and each activity includes very detailed step-by-step instructions. So the focus tonight, as John said, it's topic 3, circle and geometric proofs. And what I'm particularly interested in is showcasing the use of dynamic geometric tools to support the learning of geometric concepts and in constructing proof. Now, I think that the geometric tools are one of the underutilized features of TI-nspire, and it's a shame that they're not used more, because some of the advantages I see in using the geometric tools is that you've got the interactive and dynamic visualization rather than relying on static pictures in a textbook. Instant feedback. You can experiment, see what happens if I change this aspect or that. You can visually test conjectures, and that's one of the things we'll be doing today. So the visual verification of a proof, whilst it's not a proof in itself, can lead to greater insight in what it is that you're trying to prove, and accurate and time-efficient constructions rather than relying on freehand sketches. So in summary, I think that the use of these tools makes the learning of geometric concepts more interactive, more intuitive, more efficient, leading to deeper understanding, and I think giving students greater clarity and confidence when tackling proof. So the first activity I want to have a look at is a very straightforward theorem, the midsegment theorem, which is the statement of the theorem is the line segment connecting the midpoint of two sides of a triangle is parallel to the third side and half its length. Now, that being such a straightforward theorem, it's a good place to start introducing students to the geometry tools, and it's also a good place to introduce vector proofs. And that's what the teacher resource book does. That's how it introduces vector proof. So let's start by verifying this theorem. So what I'm going to do is I'm going to add a geometry page, and I'm going to draw an arbitrary triangle. So it's menu, shapes, triangle. Oh, what I should have said before that, I'll just escape out of there, is when you start doing using the geometry application, it's worth going to menu settings and having a look at the graphs and geometry settings. Now, these are different from the general document settings. So you can set things like the number of display digits on the geometry page, whether you want angles in degrees or radians. And one of the ones I'm interested in for these constructions is automatically label points. So if I draw a triangle, it will automatically label the points A, B, C, and so on. Okay, so back to what I was doing, menu and shapes, triangle, and because I've got the automatically labeled points selected, they're automatically included, the labels A, B, C. Now, I'm going to do the mid-segment, so I need to find the midpoints of two sides. So the midpoints are found under construction, so construction midpoint. Now, when you select a geometry tool, you'll notice that a little icon appears on the top left-hand corner, and if you move the cursor to that icon, it actually tells you how to use the tool. So all you do is click on the segment. So I'll click on each segment. And if you, whilst that tool is selected, all you can do is find midpoints of segments. So you need to escape a tool. Now, what I want to do is label the midpoints as well. Now, you'll note that the midpoints are not automatically labeled. It's because it's assuming that you may want to give it labels other than continue alphabetically after C. So you may not want to call them D and E. In fact, I want to call them P and Q. Now, the way that you can do that, the shortcut way, is just to hover over the point and then use the context menu. Now, the context menu is control menu, or if you're using the software, just a right mouse click. And you've got label, and you can enter the label. And you can move that out of the way, likewise on the other side. And now I'm going to, rather than just putting a segment between P and Q, what I'm actually going to do is draw a triangle PBQ. And you'll see why in just a minute. And so that it stands out, I'll escape that tool. I'll give it some color so you can just hover over it. By the way, this is another tip. If you sometimes when you approach a particular object, you haven't got the correct object selected. All you need to do is hit the tab. You'll notice that it says point P and then tab. If you hit the tab key, it will cycle through all nearby objects, and that way you can be sure that you're selecting the correct object. So in this case, I want the triangle. Once again, I'm using the context menu, control menu on the handheld, and color. I'll choose a fill color. I might do a gray. Now I'm going to use the transformation tool to verify that triangle PBQ is similar to triangle ABC with a scale factor of 1/2. So I'm going to go menu, transformation, and dilation. Now, how do I use this dilation tool? Well, I just go up to the tool, you click the object, then the dilation center, then the dilation value. So I'll do that. So I want this triangle with a scale factor of 1/2. let's see what that looks like. So I click that triangle, and then I just type in a half. So you just press 1 divided by 2, enter, and you see a ghosted image of ABC, A dash B dash C dashed, which is a dilation by a scale factor of a half of ABC. And we see that it fits beautifully over that triangle. Conversely, I'll escape that. I could instead have selected triangle PBQ and a scale factor of 2, and we see the image P dash B dash Q dashed, and it fits beautifully over ABC. So that's a visual verification of the theorem. Because the two triangles are similar, related by a scale factor of a half, then it follows that PB has to be parallel to AC and half the length. I could, of course, prove that using the SAS condition for similar triangles. Given that P and Q are midpoints, it means that triangle ABC and triangle PBQ have two sides that are in the same proportion and an equal included angle, and therefore the two triangles are similar. In the resource book, it's proved using vectors. So this is just a screenshot from the book. So I've named a vector U, which is vector AB, and vector BC is vector V. So we see that AB is U plus V, whereas PQ is a half U plus a half V. So a very, very gentle introduction to proof using vectors. Now, there are a number of related theorems involving midsegments, and I'm going to use some of those to highlight the use of some other geometry tools. So the midsegments of a triangle divide the triangle into 4 congruent triangles. So let's see if we can verify that. I'll escape that dilation tool, and I'll draw another I'll draw another midpoint rather. So back to construction, midpoint. I also want the midpoint of side AC, and I'm going to construct a triangle PQR. I'll just label that as well. And so that it stands out, I might give that a different color. Fill color yellow. All right, so I want to show that this yellow triangle is congruent with the other 3. Now, there's a number of ways I can do that with the transformation tool. So one way, menu, transformation, symmetry. So how do you use the symmetry tool? You click the object, then the point of symmetry. So I click the object, and so it's symmetrical about that point. We can see around whatever point, wherever I move the point, it's symmetrical about that point. So we see Q dashed, R dashed, P dashed, and it fits neatly over that triangle and that one and that one. So that's the symmetry transformation. An alternative transformation I can use is the rotation. So how do I use the rotation? Click the object, then the rotation point, then the rotation angle. So I click the object, and the angle that I want is 180. And I see that it's sort of stuck there. I sort of locked it in, so that's why it's not ghosted. I shouldn't have clicked that point because that's locked it in, but you can see that it moves and it's congruent as well. Okay, another way I could have done it is, I'll just hide that one. Okay, I don't need that point, so I'll hide that point. Once again, all I'm doing to hide them is hovering over whatever it is I want to hide, control menu and hide. The other way I could have done it is using the translation tool. So translation, so I'm going to translate this triangle. So the translation, click the object, then the translation vector. I'm not going to do that. I'm not going to put in a vector. If you put in a translation vector, then it will translate in the direction and the length of the vector. I'm going to do something a little bit different. I'm just going to keep it flexible. So I translate. You can see that it fits neatly over that one and over that one. And it makes sense, given that we know that the smaller triangles are a dilation by a factor of a half of the large triangle. When it comes to area, if you've got a dilation of a half in 2 dimensions, then a half times a half, you're going to have a quarter of the area. So it makes sense that you have 4 congruent triangles to fill the whole area. So just a few concepts coming together. All right, that's one I prepared earlier. Another related theorem is Varignon's theorem, which states that the midpoints of the sides of an arbitrary quadrilateral form a parallelogram. So I'll put in a geometry page. So select geometry. I'm going to draw an arbitrary quadrilateral. So menu, shapes, polygon, and I don't want a regular polygon. So I'm not really worried. Now, to end the polygon, there are 2 ways. You can either go back to the start and click again, or you can double click on the last one. Either way, it knows that you're done. I want to put midpoints on each of those sides. So construction, midpoint. Go. I'll escape there. Now, I do want to label them because I need to be able to know what side I'm talking about. So a quick it's certainly faster if you're using the software than if you're using the handheld to label. And I'm going to draw another quadrilateral joining those sides. So polygon again. Escape, and I'll shade that. And it doesn't matter what shape I make the polygon. It looks like a quadrilateral. If I wanted to spend more time, what I could do is go measurement. You can measure length, you can measure angle. I could actually measure each of those angles, measure those lengths, and show that it really was a parallelogram. Now, interestingly, the parallelogram, it remains a parallelogram whether it's concave or convex, it still works. Even if they cross, it still works, which is rather interesting. Now, how does this relate to the midsegment theorem that we looked at right at the outset? Well, if we start putting in some diagonals, so I'll go menu, points and lines, segment, and I put in one there. Sorry, try again. I'll do it. This is one I did earlier. I meant to go the other way. I meant to go a cross way, the other way. So putting in diagonals, we can see that the mid-segment theorem applies. So we can see the triangle. We can see the triangle DCB and RCQ, DBA, PSA, that the mid-segment theorem applies. So it's basically, once you prove the mid-segment theorem, then this one becomes obvious why these sides have to be parallel and why they have to be the same length, because they're going to be, so SR and PQ have to be the same length and parallel, and that's half the length of AC, and so on. So the mid-segment theorem in action. Okay, so some other theorems, the inscribed semicircle theorem, which is one of Thales' theorems. So the angle at the circumference in a semicircle is a right angle. So to save time, this is one that I started earlier. So all I've done is I've gone to shapes and I've chosen circle and I've chosen triangle and just made sure that the triangle was inscribed. Now I can measure the angle ABC, so menu, measurement, angle, and unsurprisingly it's 90 degrees. And it doesn't matter where it is, it's always 90 degrees. And how can I prove that that works? That's a very simple proof. The sum of angles in a triangle are 180. So if I call these two angles in red alpha and the two in blue beta, pardon me, 2 alpha plus 2 beta is 180. So alpha plus beta must be 90. And in the resource book, this is done as another simple vector proof. So we certainly see that it works. So I've defined two vectors, OA as U, OC as V. Then I express AC in terms of U and V and BC in terms of U and V and find their scalar product. When you find, this is a screenshot from the resource book, when you take the dot product, you end up with the magnitude of V squared minus the magnitude of U squared. But because V and U are both equal, because they're both the radius of the circle, then the result is 0. So if the dot product is 0, then we've proved that the angle ACB is a right angle.
Frank,
Pardon me.
Just-
Now,
we
another
just had a
one
nice
is the
comment.
converse. Sorry?
We just had a nice comment from one of the attendees about how you've used the colors and also the different styles of the lines and the shading to really emphasize some of those teaching points.
Yes, that's right. I think that if I was preparing this for a classroom demonstration, I would probably take even more time. I'm just sort of the main thing I'm trying to do in this webinar is basically introduce how you might use some of these tools, because I think that they are definitely underutilized. Okay, so the converse of the inscribed semicircle theorem. So if a triangle inscribed in a circle has a right angle, then the hypotenuse of the triangle must be the diameter of the circle. That's the converse of the inscribed semicircle theorem. So one way that we can prove that is prove that the midpoint of the side opposite the inscribed angle is the center of the circle. So let's see if we can demonstrate that. So I'm going to insert a geometry page and circle, so shape, circle, and exit that. Something else I want to point out is if you want to move an object, the whole workspace is movable. So the way that you can grab the workspace and drag it around by just pressing Control click, the click being the center of the navigation pad, or if you're using the software, of course, you just hold down the mouse. Now I'm going to I'd better label that. And I'm going to draw any inscribed, so it's not going to be a right angled triangle. I'm just going to draw a triangle that's inscribed. So all I need to make sure is that the three sides are on the circumference of the circle. And I want the midpoint of one of the sides. So construction, midpoint, and I might label that M. And what I'm now going to do, I want to measure that angle. That's something else that's important. So menu, measurement, angle, and I want to measure ABC. Oops, move that. Sometimes it's hard to pick up the right label, and so you can use the trick of using the tab key to cycle through all nearby objects. Okay, now I'm going to draw a line that's parallel to AC, but passing through the center. So how can I do that? I can go menu, construction, and parallel. Now, how do I use this tool? So click the line, then the point through which the parallel should pass. So I want parallel to this line and through the center of the circle. I'll escape. Now, to extend the line, you just go to the end of it and do Control click. Or if you're using the software, just drag it with the mouse. So Control click or drag with the mouse. I'll change some of the attributes, or I'll change the color, line color. I might make it red so it stands out, and I might make it dashed. So if I want to change the attributes of the line, just hover over the line, Control menu, attributes, and you can choose the style of line that you want. Okay, so interestingly, I'm just proving another theorem. It doesn't matter where I move B, the angle doesn't change. So I'm just sort of showing another theorem. But I'll now change, see what happens if I change, or if I drag, say, point C around. Oh, it's getting pretty close to 90 degrees there. Whoops, that's around about 90 there. Interestingly, it's when O and M coincide. So that's sort of a fairly convincing demonstration, visual demonstration, that in fact, if the angle is 90 degrees at the circumference, then the hypotenuse must be the center of the circle. But a convincing, that's one I prepared early just in case I mucked up the construction live rather than waste time redoing it. I had a spare. Okay, so doing a visual demonstration is useful, but it's not a formal proof. So we can do the proof using vectors. So it's the same sort of argument as before. I've got a vector u and a vector v, and the vector AC and vector BC I want to express in terms of u and v. When I find the dot product of those two vectors, I get the result, the magnitude of v squared is equal to the magnitude of u squared. Why do I get that? Because if I know that it's a right-angled triangle, then that's the given, then I know that the scalar product has to equal 0. So an implication of that is that the magnitude of v must equal the magnitude of u. How can that be? That can only be if they are, in fact, u and v are the radius of the circle. That will make them equal length. So we've proved that M is the center of the circle. The midpoint is the center of the circle as required. Okay, so a few other theorems. The central angle theorem proves that the angle subtended by an arc at the center of a circle is twice the angle subtended by the same arc at any point on the circumference. So one of the things I'll do here, I thought I'd demonstrate the use of the calculate tool in the geometry application. So I'll add a geometry page, and I need a circle. And what I'll do is put in a quadrilateral, an inscribed quadrilateral, and I can measure the angle, pardon me, ABC, and I better give that a label, call that O, and AOC. So menu, measurement, angle, and one of the things you notice is that it's giving the external angle in this case. So if I want to find the internal angle, one way I can do that is to use the calculate tool. Now, the way you use the calculate tool is you start putting in an expression that you want to evaluate in a text box. To enter a text box, the quick way of doing it, somewhere in the workspace, you get the context menu, control menu, text, and what I want is 360 degrees minus AOC. So 360 minus AOC, and nothing happens. But what I can then do is go menu, actions, and one of the options under actions is calculate. Now, how do I use this calculate tool? You click the expression, click each value when prompted, and then press enter to place the result. So that's what I'll do. That's the expression, and I'm prompted, select AOC. So AOC is this value here. And so it's calculated 360 minus AOC. I could also calculate other things. So for example, I could, if I wanted to know the ratio of ABC to AOC, I could put that in as well. So I could do a text box, and I'll do angle ABC divided by AOC, then go back and get the action, calculate, click the expression. I'm prompted, what's ABC? ABC is this one, and AOC is this one. So it's half the size. Now, I could go back, if I was to change that expression, I'll escape out of there. If I was to change that expression, change that to AOC and this one to ABC, it's 2. AOC is twice. Because it's not always obvious that this angle, because it's rounded to 3 decimal, to 3 figures, with rounding error, it's not always obvious to students that the angle at the center is in fact, it doesn't always appear to be exactly half or exactly twice as large. But here, where it's calculated the value to 12 decimal places, it is exactly 2. Okay. Now, by moving this around and seeing that this is always half of 140, I've also proved the other theorem, another theorem, that angles at the circumference of a circle subtended by the same arc are equal. The other thing, of course, what's the proof that these two, that the angle at the center is twice the angle at the circumference? If I call these alpha, then I've got 180 minus 2 alpha, so that must be 2 alpha. Likewise, on this side, it's 2 beta. So at the circumference, it's 2 alpha. At the center, it's 2 beta. And similarly, we can prove that angles subtended by the same arc or the same chord are always equal. And we can also prove, you can use that same reasoning to prove that a cyclic quadrilateral, that the opposite angles of a cyclic quadrilateral are supplementary. They add up to 180 degrees. So all of those are covered in quite a bit of detail in the resource book. Okay. Now, the other thing I wanted to do was to illustrate that these geometry tools are not just available in the geometry application, they are also available on the graphs application. And you can leverage these tools to enhance the graphing. So I'd like to show an example of using the geometry tools in the graphs application. And this particular one is from topic 4, subtopic 2, which involves reciprocals of trigonometric functions. But it's what I want to highlight here is not the trigonometric function part of it, but rather the geometry tool part of it. So I'll add a geometry page. Actually, I'll do this in a new problem just to make sure that I haven't got any saved variables from previous problems. So to put in a new problem in a document, it's doc, insert, problem, and graphs. So I'm going to start off with a very simple graph, y equals x.
Frank?
Yep. Yes?
You did mention it loosely, but could you just explain in a bit more detail why you went to a new problem? So it now says 5.1. What was the reason behind that?
Okay. Because I might have had saved variables. See here, if I hit the variable button, the only variable is F1, whereas I might have had stored variables from some of the geometry work that I'd been doing previously. So I didn't want any of the baggage from my previous work to carry over into this problem. So when you insert a new problem, it's like someone has handed you a brand new calculator. So basically to start with a clean slate.
Fantastic. So they can be saved as one massive document, but they're, like you said, like little mini calculators on their own right.
Absolutely. Okay, so what I want to do is illustrate what the reciprocal graph of 1 on x looks like, and or the reciprocal of sine x looks like, and y. So it's not just what it looks like. We can just graph 1 on x and we can see what the graph looks like, but why does it work? Well, this is where the geometry tool can be useful. So what I want to do is put in a point on that line. Now, you'll notice that in the graphs application, if you go to, you've got all of the geometry tools available. You've got points and lines, and in particular, you'll notice that for point or point by coordinates, it's just got a P next to it. So what that is telling you is that the shortcut for inserting a point is to just hit the key for the letter P. So if you hit the letter P key, then you can either do point or point by coordinates. Now, this time I want to do just point. So I want a point that I'm going to put on the line. So make sure that it says point on. And I've locked that in, and I get the coordinates as well, which is nice. Now, what I want to do is to store this value as a variable xc. So you just hover over it, then the context menu, control menu, store, and I'm going to store it as xc. And likewise, the other one I'm going to store as yc. So hover over it, control menu, store yc. Now what I want to do is put in a new point with coordinates xc and 1 on yc. So again, to add a point by coordinates, I just hit the key for the letter P and select point by coordinates. Pardon me. So I want xc. Now, because those have been stored, I can just hit the variable button, select xc, and enter move to the next one, then y divided by, hit the variable button, yc, and I've got the point, which is the same x coordinate, but it's the reciprocal of the y coordinate of the point on the line. So I'll just give that a different color so that it stands out. So control menu, color, might make that red. I'll also change the attribute so that it looks a little bit different. So I might choose that type of point. Now, if I now move the point along the line, we see that the point A, which has the reciprocal y value, moves accordingly. And you can see the relationship between the coordinates. So it's a pointwise approach to understanding how the inverse graph works. And we see that as we get closer and closer and closer to zero, the point A gets larger and larger because it's one on a very small number. Now, another geometry tool that we can use is geometry trace. So you can hover over the point A and control menu, and one of the options is geometry trace. And how do we use the geometry trace? Click the object, which I've already done because we started from the object, and then what it is that is doing the tracing. So as I move the point along, it's leaving a trace of where the point A has been, the locus of point A. Which is rather neat. Okay, so I'll leave it there. When you want to erase the trace, just escape, control menu, erase geometry trace. Now, if you want to automate that, you can go to the point that you want to change. If instead of dragging it, you want it to happen automatically, then control menu, one of the options is attributes. Under attributes, if you go down, you've got unidirectional animation speed, currently 0. So the animation speed can be any number from 0, which means that it's a stationary point, through to 9, which is the fastest speed. You can also have alternating animation, so it can move in either direction. Now, I want the slowest speed, so 1. So see that it's moving it's animated, moving of its own accord at a fairly slow speed, and it's got these control buttons. Now, what if instead of having y equals x, what if I had sine x? So I'll just change that to sine x. And I'll change the scale. So Windows settings, I'll change that to say negative 2 pi to 2 pi in increments of pi on 2. By the way, I'm doing this on the software, but you can type in pi on the handheld if you want to, although it's just as quick to hit the little button near the bottom on the handheld. Okay, And I might as well get multiple labels in. So just hover over the axis, control menu, attributes, and the attribute I want is multiple labels. Whoops, except I undid it. Try again, attributes, multiple labels, and enter to lock it in. Okay, so I'll start the animation. And we see that it's still working. So now I need to get a trace of that. So hover over A, control menu, geometry trace, start the animation. And we can see the relationship between the coordinates. The X coordinate is the same for both points. The Y coordinates are reciprocals of each other.
And Frank, that's a beautiful visual, isn't it? Especially with the animation.
Yeah, I think that it's certainly a lot more meaningful to students than just doing the graph of cosec, and by magic, that's what the graph looks like. So I think that's a pretty good and it's pretty obvious why you've got those asymptotes happening. And that's why I think it's probably a good idea to start with something simple like 1 on x, where it's really obvious why you've got an asymptote at x equals 0, and it works similarly in these cases as you approach 0. 1 on a very small number becomes a very large number. I can then escape there, go up to F2. I'll move this out of the way, and let's choose cosec.
Frank, someone asked, how did you get up to F2 so quickly?
Oh, okay. Now I just double click on the workspace. So, I mean, there's a whole lot of ways you can do tab. But the trouble with tab is when you've got objects, like if you have sliders, or in this case the control, it cycles through all the other objects you might have there. So tab is not always the most efficient. Control G is fairly efficient, but I find that the most efficient is to just double click on the workspace.
Fantastic, thank you.
Okay, and so what I wanted to do today was to showcase a number of geometry tools, and in particular show that they are available not only in the geometry application, but they can be used in conjunction with graphing, and you can do these sorts of things, which just makes the graphing application a bit more powerful. So I think before I start coughing again, I think I might leave it there, John. So thank you very much for listening.
That's fantastic. No, absolutely fantastic. It was really nice. One of the responses from one of the attendees was, it was a technically demanding webinar, handled very well. So I think that people really appreciate that, and from the feedback in the chat, that's what they were saying. I think the way that you use some of the transformations as well to sort of move the shapes around and see how they fitted, whether that was dilation, symmetry, and rotation, were fantastic. So Frank, a really rewarding webinar, so thank you very much for your time on that one.
Thank you, John, and thank you everyone for attending.